I sound.
A long and beautiful.
This is a beautiful journey. We're just starting. I feel like I'm like reality TV. Oh, it's my journey. This is my multidimensional journey.
Sounds like a TLC show.
It does, exactly.
Right.
My multidimensional life. Oh, there you go. Undercover multidimensionality, something like that. All right. What about when multiple dimensions are bad? Well, how do you figure them out? First of all, what are they? I just challenged the idea of whether or not a dimension, what we use for it, is very prominent. This applies to many of the large-scale assessment situations we're all in ed measurement are unidimensional, and so this is, I feel like, the predominant attitude, even though it was not the world I grew up in research-wise. And one of the historical problems is that some of the ways that we would talk about dimensionality don't always. They give us a result, but that's like, is that contextual to the method we use? Case in point, if I were to ask one of you, hey, I don't know, Fonzo, here's some data. How many dimensions in it? And I tell you nothing else. What would be the first thing you thought to do? Picking on you, I'm sorry.
A picture?
Take a picture? Yeah, a picture of something. What would you like here's a bunch of item responses, like 30. I have a 30 by 1,000. Like 1,000 people gave me 30 responses. How many dimensions do I have? What would you picture? No idea. Anybody else want to throw in?
PCA.
A PCA. Yeah, there we go. Principal components. At least that, all right? And you might plot the picture of the scree plot. All right, you've heard of that before? Some problems with that, though, right?
They all load onto the same time.
Well, that happens a lot. There's usually a strong mean effect. But exploratory factor analysis itself is sort of problematic for determining dimensions, even if those are how you're defining your dimensions. So principal components is one version of it. There's a whole bunch of methods that came out 1930s, 1940s that we still use today to do this job. But what are we doing PCA on usually, right? We take the data, we usually create a covariance matrix or a correlation matrix, and we go and take the eigenfunction in R and get a bunch of eigenvalues, eigenvectors. Have any of you heard of this before? Okay, great. Except that covariance matrix, if these were binary items and we're using a Pearson covariance, like the Pearson correlation, we have a big problem in that Pearson correlation doesn't have the full range under binary items unless very, very narrow conditions are met. Margins are equal and they're equal to 0.5 of binary data, of a pair of data. So EFA, that's one of the problems. The data doesn't always match. Sure enough, I have to think that screws up some of the results. The bigger thought is, if you believe there's one dimension and you have one model, why do you use a different method? This is why model fit, by the way, shows up first, right? Would you prefer, let me ask you this, and you've probably seen this before, probably done it before, I had to, all right? How many of you have said, okay, I built an assessment, I'm going to use a unidimensional model to score it, but I'm going to use PCA to figure out how many dimensions are in it. Right? So I'm going to do a completely different model altogether to figure that out. Right? If you get a different result, then you now have a confound. Is it truly the right result, or is it potentially because you use different models for the same approach? Right? So that's yet another question to think about. Turns out, let's imagine you have continuous data and you use exploratory factor analysis, PCA, if you will. There's two types. We don't talk about a lot of them but the principal components version is the matrix decomposition, where we take a matrix and we do math on it and we get stuff out of it. All right, fine. What we're doing is taking that matrix and breaking it into a series of numbers and vectors that go with those numbers that sort of give you parts of the information of the matrix itself. So basically, if you remember the Cholesky, I mentioned this before, the Cholesky is a reorganizing of a covariance or correlation matrix, a diagonal or a symmetric matrix, into a triangular form. It contains all of the same information such that you can always go from one way to the other. Principal components is another type of reorganization like that, right? We're now taking the information of a matrix, and instead of making a triangular matrix out of it, what we're doing is getting a series of numbers, single numbers called eigenvalues, and a series of vectors that correspond to those values, such that the vectors themselves, or if you were to take the linear combination of the vector with the data, or another principal component of it, that linear combination was independent. Blah, 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 blah.
Random question, is QR decomposition doing the same thing?
As Cholesky.
Okay.
Yeah.
Okay.
And QR does it a bit differently, but it's more robust in certain situations. So, QR, by the way, Alan Turing created. So, I don't know if you know Turing from the Enigma code, the World War II famous Bletchley. Yeah, that's right. The Bletchley Park in England. Anyway, so that's one version of it. This matrix decomposition are really, they're very unstable. I know it sounds weird. We don't teach you this when we teach you PCA. At least if I teach you PCA, you'll get it. But like if you try it with a simulation, like simulate data and throw them in a principal component, see how many eigenvalues are bigger than one. It'll vary, like whatever your conclusion is. So it's very unstable. So that's one problem. The other problem, if you choose, okay, so forget the matrix decomposition. I learned something called maximum likelihood. Let's do maximum likelihood. Turns out there is no such thing as maximum likelihood exploratory factor analysis. I know that sounds crazy because we have it and people use it. There's a proc factor in SAS that'll do that for you, like by default. It puts in a series of constraints on the model to estimate it. That series of constraints is no different than setting a series of constraints in a confirmatory factor analysis. They're different for constraints, but you still have the same number of them to be able to identify it. So therefore, maximum likelihood-based exploratory factor analysis isn't even exploratory in the first place. And sure enough, if your data don't meet the assumptions, the constraints, which are these weird, strange assumptions. In fact, if you go into SAS's user manual, you can't even find it. They reference, was it a book by Lawley and Maxwell, something along those lines? A 1970s textbook. I had to go find it one day to look at it. And like buried in there, the constraint is this: the product of the factor loadings, the vector of factor loadings times the unique variance matrix times the vector of factor loadings transpose has to be a diagonal matrix. Those are your constraints. If you caught did anybody understand what I just said? I said it so quickly. It's like, if you didn't understand that, that's fine, because most of us don't understand it. But they don't even print that in the manual of SAS. That's going on behind the scenes. That's crazy, right? So, anyway, long story short, EFA is hard. This is the factor analysis version. I don't know that I'm going to go much into this right now. This is the taking my word for it. I'll get to this later in the semester, because later on. So, it's hard to determine how many dimensions there are, is what I'm getting at, if you're using so-called exploratory approaches. EFA was like the first chat GPT. Hey, EFA, how many dimensions are in my data? What am I measuring, right? And of course it'd come back, well, it looks like your data have 3 dimensions, and here's what, like it's just like, but it's not accurate, right? I'm sorry, I'm gonna be like, yeah, chat GPT, not that accurate. Of course, Sergio, we didn't train it correctly, but a different version is to build likelihood ratio tests and approximate fit indices. The other thing that would surprise me when I got into my career was that people would, there are a bunch of journals out there that publish reports on brand new assessments. Like there's a journal called Assessment. And in that journal, people will basically talk about the development and validation and testing of an assessment, whether it's in education or in psychology or whatever. I remember sitting on, I think I was a reviewer for it, and I kept getting these papers that were like, well, I did a CFA, I did an EFA, and then I did a CFA to determine how many dimensions I have. And I was like, why are you doing the EFA part? Because the CFA is the methodology that you want to use. So a more appropriate approach is more confirmatory. We're going to learn that in this class. CFA, multidimensional IRT. Basically, you fit the model that may be the dimensionality you think it is, and you test whether that model fits the data. Right? So if you believe there's one dimension, if one dimensional model doesn't fit the data, you know that there's not one dimension. You can't go any lower than one. There may be some other issue with the data, but most likely there's more than one dimension. If you think you have two dimensions, you fit a two-dimensional model, does it fit the data? Good question. Those types of things. So that's why what you're seeing in the next couple of weeks are the tools to do that from the get-go, which is the measurement models themselves, which is next week, the model fit, which will be the week after that. All right. So why would we want multiple dimensions? And again, I'm going through this quickly. This is like high level. The way I structured this class with 80 minutes for lecture, they're going to be snippets of lecture. They're not going to be the depth. They're going to be enough to cover it and to get us to talk about it. And then I expect with homework, if I give you the right type of homework, you'll practice and learn more about it. So I should mention that if you're looking for the depth of knowledge from lecture, it's probably not going to happen this semester. I don't know that it happened the last time you taught. You took a class with me anyway, but still. I think there are good reasons for multidimensional assessment, particularly in education, particularly if you think about classroom assessments, formative assessments, what students are learning, right? We get additional information about student abilities. Right? We get a profile of scores for a student. Sometimes, depending on what you're measuring, you may need more dimensionality. What do I mean by that? How many of you, a lot of you worked at ITP, Iowa Testing Programs. You're working on the Iowa State Assessment, ISASP. Like you've got math as your score, right? Say math score for every student, you may have some sub-scores with it. Something like that? Am I in the ballpark?
Yeah.
Okay, got it. That's a really high level score, right? It's just math. Let me give you the alternative to that. That is one where every item, by the way, measures math. It's all math items measuring math. That seems, again, high level. What if you were trying to measure something more nuanced, like rules of exponents in algebra? Something along those lines, right? Now you're probably talking multiple dimensions because understanding exponents is a pretty complicated set of rules, right? How you add them, the product of exponents, what that implies, sort of the algebra of the exponents themselves, inverses, all those things could be dimensions. And here's the problem. As you get more narrowly focused on your score, it's harder and harder to write an item that only measures one dimension of it, right? So if you can write, can you come up with, I was saying exponents, we can go to, let's say, proportional reasoning, something like finding a common denominator, or I don't know, reasoning about what a proportion refers to. What's the full unit it's referring to? Some really nuanced math education features. It's very difficult to write an item that only measures one thing. And that's the one thing you've probably been taught. In other classes in educational measurement, you've probably heard a good item is an item that measures only one thing. How many times have you heard that? Yeah. Is that George Englehart? Oh, geez. See, I disagree. I don't think that's necessarily the case, and you're not going to see why. I don't always agree with that. It may be the case that a good item, what a good item is, depends on what you're trying to measure in the first place.
It was an introductory class.
Yeah, the introductory classes, we always say things like that. Like, oh, a good item measures only one thing and all this other stuff. But if you think about it, the more nuanced the target of measurement is, if I'm trying to give you not a score about math, but a score about how you're going to find the lowest common denominator, it's very difficult to just find the lowest common denominator and not do something else with a fraction. That part of it is going to be included in the score if we don't model it. And that's why a good item may be impossible to write only for one thing. Right? That historical context of a good item is an item that measures only one thing is fine if that one thing is a very high level, gross level measure, like mathematics itself. Right? I'd actually challenge you that word problems aren't measuring mathematics only, right? That probably measures two things as well. So again, yet again, it depends. All right. The other thing that's interesting in ed measurement is that the way that we build assessments is oftenly a multidimensional process. When you write, do you guys write items in ITP? I don't know if that's part of your job. You don't do that, but other people do.
Yeah.
Have you seen their process? I don't know. I used to work at a... Oh, you got the technical manual, yeah. Well, I used to work at a testing center too, right? I've worked in operation assessment before, and the folks where I worked, they would be writing items with domain or standard or whatever information that needs to be written for the item itself. You come up with a blueprint based on standards. If you go look up state assessment blueprints, you'll see a number of items per standard. It's almost like saying the standards are really the dimensions. How are we sort of forgetting that and just doing a unidimensional model on it? That's the disconnect I have. So it's an interesting, like the focus of multidimensionality, because ed measurement, the hypothesis I have on this, because ed measurement has this big industry, this field, and I'm not going to say that I hate the industry, but because it's built the way it has, there's no inertia or motivation to change it, so everything looks the way that does because of that. Whereas if you're not in that industry or not tied to it, science is very different from it. And thinking about it from a critical lens or a philosophical lens scientifically might lead you to a different way of doing practice today than you see currently in what we do. So anyway, here's an example for you. This is an item where I had a math item that was a word problem, right? So in your state assessment, every student from 3rd to 8th grade has to do the math and the English language arts in our state, and then after that in high school once for each, if I'm not mistaken, at least that's the federal law. This is a math item that was a word problem where I added in calibration with their ELA score. So we have a score for reading. We're not using it in our assessment of the math, and this is what happens if that person if there was an interaction between math and reading on the item itself. This is actually a latent variable interaction on this plot. We're going to get to that later in the class. But what I'm talking about here is each of these lines represents a student with a different sort of low, average, or high reading score. And the item characteristics might vary as a function of a person's reading score. Now, we wouldn't know that in the way we calibrate these. It's just, you don't give me the side eye.
I don't like this because there's also things like their study habits. There's too many factors. I don't like this slide. Sorry, that is what.
This slide doesn't like you.
Neutral.
Dang.
Sorry, that's what you.
Well, I was going with the opposite, right? I'm saying, I saw the side eye look, and I was like, the side eye like emoji look, and I was like, that's going on. You were sitting up front, so I saw the eyes. I don't know about that. I was actually going with this, right? In ITP, do you guys does party work give the scores? Do you do? I don't know.
That's all done before we get.
You don't do that either. All right.
We're just doing research.
Okay, cool. So I'm not trying to pry. I'm trying to put this in the context that's familiar.
Sure.
Okay. At KU, when I worked in their assessment shop, we did the state assessment at Kansas, in addition to a national dynamic learning maps assessment. I worked on the latter. But when you think about it, in the state assessment program, we would have a set of scores for ELA and a set of scores for math. And they were separately calibrated and separately built. What I'm arguing is you multidimensionally could have something like this going on, whereas if you're saying, hey, we know reading is an important factor in students' understanding of mathematics, word problems, you have all the data to do it, but you don't actually estimate it, right? It's one of those things where it could be multidimensional. Now, does that make it more, is my argument convincing you? And you open my weakness. Cheez-Its. Sorry, no, I don't. Oh, Cheez-Its. Somebody opens a bag of gold. I eat like a third grader.
I see what you mean with how reading can change, how they read the problem.
Yes.
I still don't like this thing.
Well, let's think another way. We're taught in psychometrics, this is a thought experiment. We're taught in psychometrics about construct relevant variance and irrelevant variance when it comes to differential item functioning. And we want an item where there's construct relevant variance. It respects variation on it. But if something apart from that, this is like saying this item has diff based on reading, is what I'm trying to say. Like if you didn't know what a person's reading is, we're not measuring math only with this, is what I'm saying. Go ahead. No?
This is a test, right?
Yeah.
So
It's
there
hypothetical.
are items that have more reading than others. So
Yeah.
if you were to do this, wouldn't you only want to look at the word problems? Because not all of
Right.
them are word problems.
That's correct. That's exactly it. So you go down your
You're
math.
looking at 2 entire tests.
This is a single math item, a single word problem. This is right here.
A single word problem.
That's
so
right.
It's not an entire test.
That's right.
So
It's a single word problem.
It's like you're saying that for this problem, if you consider their reading ability, you'll have more information.
That's exactly right. Or,
Their math
oh,
ability.
that's exactly right. Or what you need to do is control for their reading ability to
So
be able to
feel
get the
a
math
little bit
ability.
better about it knowing it's only one word problem.
That's it. Not the entire
I
assessment.
thought it was the entire math score.
Oh, no. You wouldn't do this on items that didn't have words to it. And that's important because you can't estimate reading and math on every item for the whole math test unless you have a bunch of reading
I
items
feel a little bit better about it.
that don't do that. So this, by the way, when we get to the confirmatory models, you all are going to do that. In the data sets I'm preparing for you, there is math and there's reading. And we're going to test this type of stuff too, in formative data. So it'd be kind of fun. Anyway. All right. What are the benefits of multidimensionality? More information. I'm interested this year, by the way, in this is with my kid going to 3rd grade. It's the first year he's doing a lot of assessments and stuff. So I'm interested in having those conversations with, with teachers. I've already had people, the Region 10 folks were like, oh, are you going to be one of the people that complain about tests to teachers? I'm like, no, although I did actually. I was talking to a superintendent once.
So we did.
I was in Olathe talking to the superintendent there, and I was talking about assessments and reliability, and I was like, well, my daughter took this one test, and I said, like any good parent, I went to the technical manual, and he falls out of his chair laughing, like, no, I did, and it was like I could see the teacher was saying and my daughter was struggling, and I'm like, actually, based on the reliability, she's somewhere between the lower end and the upper 70, in the 75th percentile. Really? Like, yeah, really. That's how wide the interval was, right? So, anyway, point being, where we're going.
Well, I spent 30 minutes once talking to my therapist right before her kids took the Iowa State assessment about how the tests aren't built for the purpose of actually judging individual kids.
Yes,
So the teachers shouldn't put so much pressure on the kids doing that.
that's exactly right. That's exactly right.
And she was like, thank you. I'm like, yeah, you should be paying me right.
At the end of this class, maybe in the final, I'll ask each of you for your opinion on this. Should I have my child opt out of the Iowa State assessment? The reason why I say that is, let's be real. I understand the need for accountability, but you're wasting my kids' learning by doing it. And the only remedy I have to that is to pull them out. So, anyway, I need to homeschool them that week or something along those lines. It's probably not going to go well. I will probably let them take the test.
It helps them work on test taking skills,
Yeah, that is true. All right. Turns out there are some benefits from multidimensionality. It's surprising. If you have a unidimensional assessment, you can quantify, let's say, reliability or standard error of measurement, right? That's one thing. Turns out if you have multiple dimensions and they're correlated, you borrow information across each dimension. Meaning, let's imagine we have the math and ELA calibrated together, but not with this item. Let's just say there's math, there's ELA, and there's a correlation between the two. They're going to be highly correlated, right? If we did that, that means each item is directly either measuring math or it's measuring ELA, but it's indirectly having impact on the other score based on characteristics of the data. This is sort of a Bayesian idea. But this is a slide from a paper from 2013 with Laney, with Bradshaw, that showed this. I was a little bit surprised by that, but the lines at the top are multidimensional assessments, the lines at the bottom are unidimensional assessments, and this is reliability, so the average reliability of the assessment itself by items per dimension. And what you can see there is if you're in a system, in a situation where you've got joint calibration of multiple dimensions, you'll have borrowing of information, so you'll be a little bit more precise on the dimensions that you're not measuring. Where this might be impactful will be some of the data that you're working on with right now for this class, the formative assessment data. If we're trying to give you 4 scores about what you're doing in October of a school year, but we don't have that many items for each, they're not going to be highly reliable scores. But if we estimate them jointly, we might be able to get a little bit better reliability based on patterns in the data itself, sort of that covariance of factors as it goes through. So this is one of the benefits of multidimensional assessment, is that you are, in a limited sense, able to get more information. Now, the flip of that is, should we really be using it? Because if you think about it, in a high-stakes test, why we have better reliability is the correlation between dimensions. That correlation doesn't only come from a single child, though. It comes from the whole sample, right? It's a factor covariance matrix. So now we're saying that a student's score or a student's conditional standard of error of measurement may depend on more than this them taking the assessment. But in low-stakes cases, I think it's okay. But that's something we'll talk about later on, too. Fonza.
In the graph here, the DCM has higher reliability, whether it's 1 dimension or 3. So we get better precision if we don't assume a continuous.
Yeah, that's actually one of the other weirder things, right? So why this is all important is to measure multiple dimensions takes a ton of items. And one of the remedies to that was to say, let's measure those dimensions really badly. And that's what a DCM does. I know that sounds bad, but that's exactly what it is. It's basically taking a fuzzy version of a dimension. And because of that, it's a lot easier to classify people. Now, the other flip to this is, this reliability measure is somewhat comparing apples to oranges. Because reliability in a continuous variable is different than reliability in a discrete variable. So I wouldn't put too much stock on that. The bigger picture of why I'm talking about this is the phenomenon that the multidimensional models uniformly have better precision when jointly calibrated compared to unidimensional models itself. But I'll come back to that when we talk DCMs later in the class. Yeah, DCMs are, as I mentioned, what did I say? Bad multidimensional, fuzzy multidimensional models is really the way I look at them. Okay, but there are, so that's some of the benefits, not just multiple scores, a little bit better precision if you're doing it in a joint calibration context. In low-stakes settings, that might be very important, particularly trying to figure out how students are learning throughout the academic year. That would be a really important thing. There are some drawbacks, though, right? I just mentioned one. Like, if you think it takes a lot of items to measure 1 dimension, imagine measuring 2, right? Licensure and certification exams are a good example for this, right? Like the NCLEX, my family, a bunch of nurses. They use the nursing board is something called the NCLEX. Some of your former colleagues work there, where it's somewhere in Chicago. I can't remember the name. Anyway, they use a computerized adaptive assessment, and the minimum number of items they give out is over 100, with the maximum being somewhere in the 300s. Right? That's to measure 1 dimension well enough to have the precision to have a 95% confidence that the person's above or below where the cut score should be. Right? That's a lot of items for 1 dimension on a really critical assessment. Right? We want that assessment to be really reliable and accurate, so that's why it's good. So now think about that, and I want you to measure 4. Oh, thanks, Siri. Siri's working on that. Thanks. Anyway. I love my devices until they start acting up, and then I have to put them in timeout. The measuring more than 1 dimension well is really difficult, and it takes a lot of time, a lot of items, a lot of effort. So that's where other approaches like DCMs have come in. That's important. The other, I said challenges that are able to be overcome. Estimation's also a problem that's difficult. We'll see that pretty soon. Challenges that are difficult to overcome is, like in education, dimensionality could be related to age, opportunity to learn, and potentially other group characteristics. Not only that, you could create a multidimensional assessment all you want, but data will be the ultimate guide. Right? If you estimate a 2-dimensional IRT model on data and the factor correlation is 0.99, you probably don't have 2 dimensions, right? They're so highly correlated. So those are problems we can't get away from, right? If you're measuring basically the same thing multiple times, doesn't matter which method you use, it's going to be the same thing, right? That's hard, very hard. So the dimensions must exist. This is one where I do add up. Finally, this is the preview of the subscores. The subscore discussion is very interesting to me. So again, the subscore in a large scale when we're selling thetas in a large scale world, a lot of times you'll get a testing program calibrated on one dimension, but then you'll see the subscores as well. Turns out, when you do that, this is a plot. This is the number of items in a subscore. The dashed line is the true score. I took a unidimensional model. I generated it with 4 times the number of items per subtest, just to show this phenomenon. Each of these lines is the average value for a person's subscore. Do you see a trend? They converge to the unidimensional score with sufficient numbers of items. Basically, a subscore, when you have a unidimensional model above it, is a short form of the same test because the model doesn't care. All right? So if you think about what a lot of educators want to know, now I haven't been in a classroom, some of you have. If you ever got test scores back, a lot of the people I've talked to are like, oh, I want to see the subscores. Turns out the only time we have variation is when we have a small number of items, and that variation is likely chasing noise. Right? So literally, I will show you this simulation last week of class and what I'm saying about it. But this is why when you see subscores, like in state assessments, or if you have children that come back with assessments and they're looking at those subscores, those are just usually garbage. They're chasing, if there's any difference in the numbers, they're chasing noise because they have short versions of the overall dimension itself. Something to think about. I see thoughts in people's heads. Is this thought-provoking a little bit? I don't know if you thought about it. But subscores, by the way, to be fair, most of the people in the biz of selling thetas that I know also hate the subscores. They hate it with passion. Well, they turn around and will say, but I got to keep my client happy, right? Well, this actually brings up a unique combination. If these are, let's say these are domain scores or something along those lines, like numbers and operations or algebra, algebraic thinking, geometry, measurement, and data, right? Those are domain scores. A flip to this subscore, right? This is from an assessment program that uses a unidimensional model to give you a math score. The flip, if you really wanted the subscores, the better way of doing it is to estimate the subscores directly as a multidimensional model and then form the unidimensional model as an aggregate of that. Right? That's the key. Right? You can satisfy the state or your client. You just have to change your assessment approach, your modeling approach to be able to do it. And we'll talk about ways of doing that as well too. And now that still may not be possible because dimensionality has to be present, but anyway, that's what I'm thinking. There, did I tie into your hatred a little bit? Okay. I have been there. I was there at Kansas. We had a colleague, Mary Ann Perry. You may have heard of her name. She worked at Senator Assessment. She's at Kansas. She's now at West Ed. And she was talking about, she was director there at the Kansas Assessment Program. And she was saying basically that in one of our seminars. Like, what do you do if your client says, I need this, and you know it's not going to be right psychometrically? I tell you what the answer was, we need the money. Right? But it is a delicate situation. All right, I'm all done. But this is an overview. Ironically, I ended with subscores. I didn't look at this prior to building my list of like topics for this year, and I'm like, gosh, I did think about this a lot. It's been put together a lot from there, so that's where I'm at. Any questions on any of this stuff? Yeah, Vladimir.
What kind of items are you using there?
In this case, these are binary items. Yeah, like this. If this was like an achievement test of some sort.
Could we use another kind of items?
Oh yeah. It doesn't. These are the thetas themselves. So if we had a blend of binary, constructed response, so forth, that'd be fine too. Anytime. Other questions? Okay. Lecture has closed for now. This is always weird. I always have these great ambitions of trying something new every class. And I do try something new every class. The problem is it usually falls on its face. So now is the something that's new. How many of you brought computing? Most of you did, right? Let's talk about the high performance computing setup. That sound good? Glam. Love it. I wanted to go here.
Were you able to make containers
Yeah.
using that?
I did, yeah, thanks. Thanks for that code. I really appreciate it. Now, today we're not going to do containers, though.
Okay.
We're going to do the beginning of, next week we're going to have the containers. So here, let me give you what's in my head, right? Today was get to know each other, get to know what the class is about. Next week is we're getting into stuff you probably already know, but to form our language the same. IRT models, measurement models, so forth. And then next week we'll get into more of the analysis online. So we anticipate having a little homework, run a quick data analysis online. But Argon is really what I like to use, and I have here, nope, try that one here, nope. Okay, trying again, sorry kids. Why I say that? I've been around the child too much. There we go. I have another set of slides for you here today. And these are an example. These are slides to teach you a little bit about Argon itself, the high performance computing system. So actually, let me close that. Ding is right. And that. Let's see here. Where'd it go, man? Well, okay. I can fix this. So these slides I gave in a class a couple years ago. I'm just going to hit the high points of them. And ironically, I somehow deleted all my class notes from that year. And I could only find the PDF, and it's killing me. Like, I made these slides, but this is something I borrowed before. Let's talk a little bit. How many of you have used Argon before? Many of you, but not all of you, right? We talk a little bit about the structure of the high performance computing system real quick. Okay? We'll go through this fairly quickly. There is, in the basement of this building, in the South Linquist, if you go out the first floor, you'll hear a bunch of fans. That's part of the high performance computing system is in the basement. If you ever get a tour of it, if you're like me and love all the devices, there are racks and racks of servers. They have giant cool rooms, and they have places where they pipe the heat out of. It's super cool, like engineering-wise. It's awesome, all right? But I digress. We use a high-performance computing system or a compute cluster to do a bunch of tasks that need lots of computation. It's a large number of computers that are linked together. They are blade-looking servers. If you've ever seen pictures of like internet shops or whatever, that's that, right? So it's a large number of computers, software that allows them to work together, and a tool for solving computational problems that require more CPU or memory that's on your single system, right? So this is really important in multidimensional measurement for a lot of estimation, because the number of calculations that are needed to do things in a good estimation sense are so high it takes a long time to do. High performance computing is often what we call. This is a way to use multiple computers coordinated together to solve a single problem. That means we could have tens to thousands of what are called processor cores. So if you look at your computer, there's the part called the processor that does the number crunching in layman's terms. Many of you may know more about this than me, so that's fine. But in your system, do you know how many cores you have in your system? I'll bet you do. 8?
Actually, I don't know for this time.
That's right. Anyway, not something you think of a lot, but each of those is like a separate processor, right? So the fact that I'm recording this lecture and I'm showing you the slide and it's going on the screen, each of those needs different bits of computing to do its job. Those cores are separate in a sense that they are able to, one of them could be dedicated to running the video, one of them could be dedicated to doing the recording, those types of things. For us, in those cores, we might need that to do computations when it comes to estimation. Similarly, each of the computers in here are likely to have somewhere up to maybe 16, 20 cores. tops. Many of your computers will have 4. Just say that you have 8. I know that machine. You've got an M1 MacBook Air, 8. 4 high performance, 4 low performance, but still.
12 cores, 20 threads.
Oh, very nice, very nice. See, I don't know, I haven't named this one yet. This one has one of the max chips of the N1, so it's got a little bit more, but anyway. The other thing that you have in your computer is RAM. You probably heard that term. What does RAM do? Anybody?
Random access memory.
Yeah. What's it do?
So it stores things temporarily.
That's it. It's quick. It's not like a hard disk. A hard disk is something that takes a bit of time to write to. In this case, a solid state drive is usually what we use these days. It doesn't take that much time, but it's different. Both store things. One is meant to be accessed much quicker. That's the RAM. One is meant to go slower. If you are on your computer, you probably may not think about how much memory is on your computer. You have 8 gig, actually 16 on yours. But the amount of memory is somewhat, when we're using desktop computers, if you run out, in the old days, it would just break. It would just stop, right? They've tried, now that we have better hard disks, what ends up happening is they sort of take some of that hard disk space to put some of the stuff that should go in RAM in. So it doesn't usually break. So you don't normally see it, unless you're doing something really intense. If you like video games, if you like, multidimensional IRT models or something like that, right? That is where you might see an overload of the memory itself. Anyway, Argon has some 25,000 cores now. So if you think about it, you have how many? 12? 12, right? So you could do something with 12, but if it outstrips or if it shuts everything down or it makes it so hot it wants to melt, not good. Argon now can come in and be like, you know what, forget it. I've got 30,000 or 20,000 that we could run it on. Now you're not going to use all at the same time. It's shared, but you're able to use it for that. And then you need a way to bring it together. That's something called MPI is one of them. OpenMP is another. This relates to how computers that maybe link together in network work on the same problem together. MPI is across different machines, so they don't have shared memory, right? So if you think about it, Sergio and I decided to create a computer cluster out of our computers. His has its own RAM. I have my own RAM. I need a way to be able to get my information to his and back and forth. That's this. OpenMP is the opposite. It's multiple cores with shared memory. So like it would be on your local machine. Both show up. But you see this, and if you go to one of these slides actually came from one of the Argon workshops. They talk about, computational fluid dynamics, molecular dynamics, all these things. And I'm like, yeah, what about psychometrics? We need this. So this is a good skill to have. Use high performance. There's another, they make a distinction between something called high performance and high throughput. High throughput is like a simulation study. You have a lot of analyses to do, but any one of them doesn't take a whole lot of time. Right? So if you have like a simulation that's fairly straightforward and you want to do 1,000 replications, right? Waiting for 1,000 turns of an IRT model would happen on your laptop just fine. It would just take a while. But you could, on Argon, you can take all those 1,000 and get them started simultaneously. Maybe not all 1,000. Like they'll have a limit as to how much space you can use. Usually it's in somewhere between 60 and 80 at a time, running at once. So either you use the high performance computing because you need more resources computationally, or you need it because you need to take a large job and cut it into parts to make it move faster. But that's another example of how to use it. So this is our Argon. I was wrong. This was from 2019. There were 14,000 cores. Each core, by the way, has we call it hyper-threading. I don't know if you've heard of it. It's like a miniature core within a core. So it's like doubles the number that you end up having. And each of the blades have up to like 512 gigabytes of RAM. Now, a ton of what we do, because of the large language models, because of all the machine learning, we end up using a lot of graphical processors, although in our class we won't. I haven't gotten there in my studies yet. But a lot of what you'll see on the Argon system is now graphics cards. And the same reason. Graphics cards are great because they actually have a ton of cores. Ton, right? To display graphics quickly on a screen like in a video game. But that actually makes them really good for tasks that we do computationally in psychometrics, where we have to divide things. Let me give you an example. If you have a graphics card that has, let's say, 1,000 cores, and you have 1,000 people in your data set, each one needs a theta. You could estimate all their thetas simultaneously, one per core. It goes much faster that way, you would imagine. So, I don't need to know all that. Okay. All right, how many of you are ready to access Argon? Okay, you've already done it. Here's the problem. To access Argon, you need a terminal window, and you need something called SSH. Secure shell. Secure shell. I sound like I've been drinking. I probably have been drinking. So, yes, question? No. Okay. Adding on about my drinking comment. So if you want to access Argon and you're on a Mac, anybody have Linux in here?
I tried.
If you got Mac or Linux, yeah, Linux you got to have a lot of patience with. It's like the multidimensional models. You can just go to your terminal window and type SSH. If you're on a Windows machine, you need an SSH client.
PowerShell works too.
PowerShell can have it, but not always. And what I would say, how many of you have that? How many of you have Windows machines? How many of you have SSH on your Windows machines? Many of you may already have it. Yes? So I'll show you this. If you don't have it, actually the thing I would recommend is installing the Windows subsystem for Linux. Have you seen that? WSL? It's a quick thing to install. This Windows subsystem for Linux, you can quickly install it by going to a command prompt and typing WSL-install. And that will install it. The Windows subsystem for Linux, turns out it gives you on your Windows machine a miniaturized, virtualized Linux system. And Linux has SSH built in. You have a look, Nathan. What am I missing?
Well, it's WSL's a little bit. Putty works most of the time.
All right.
Windows is just not good for.
No.
No.
Agreed.
I'm so tied to it.
I made the switch in 2016 because of the same reason. So, if you'd like to do this, if you're enrolled in the class, I don't know about the guys that enrolled yesterday. I think, Alfonso, you have an Argon account. Mubarak, you have an Argon account? I don't know if you do or not. Everybody has a class account, I'll say that. So what you can do to log in is go to a command terminal. If you're on Mac, you hit command space and type the word terminal. That's the one to go to. If you're on Windows, you're on your own. Sorry. And then you type SSH, you type your Hawk ID, mine is J Templin. If you type mine, you're not going to get in.
Key minus T40.
You can.
Is that necessary?
On campus, no.
No.
If you're on, so I'll get to this in just a
Okay,
bit.
sorry.
We're all on campus. Just type SSH, your Hawk ID at argon.hpc.uiowa.edu. Can you see that in my screen very well? How's that better? Well, I'm not sure I can make it. How's that? Better? SSH Hawk ID at argon.hpc.uiowa.edu. When you do that, it'll ask you for your password. This is your Hawk ID password, like you would to sign in to any campus system. You gotta remember mine. 1, 2, 3, 4, 5. Hey, it worked. All right. Then you'll ask your Duo Mobile push. And get your push notification on your cell phone, and it takes a moment, but it will log in. Oh, wow. Would you mind handing me the paper towel, please?
Oh, there's a couple.
Thank you.
Yes.
I wasn't going to let you get hit in that.
I'm enjoying my softball team.
That's right, you have the softball skills. Thank you. All right, so this is Argon. How many of you got in? Okay. Now, Annette, do you have an Argon account from before, or is this?
Well, all we did was log into Base, didn't we?
Yeah, that's right. But you didn't sign up for one outside of the class, did you?
No.
Okay, so good. That means the class accounts are working, so I can't test that. Are you in? Okay. Anybody need help?
Sorry.
Yeah, questions?
If I never use it, so I should apply. I should apply the account.
Oh yes, if you have never done this before, it'll say you're connecting to a new machine, type yes. That is, if you're connecting to machines, sometimes people hack into machines and change their signature, like change the machine they're at, change the routing to it, and that keeps you from it. So. Okay, yes. Uh-oh.
I don't know what's going on with this Mac. Things just started freezing on it, so I was trying to just shut it down and reopen it. But I don't
Except for the
have
people who won't let me. That happened to me last week.
Oh yeah, I remember that.
Yeah.
All right.
It's never done this.
It doesn't
There you
happen.
go. So just put your, it's working again now. I don't know what happened.
But we never was like,
No, it's.
it was a PDF I was on, and then
It says that
In order to like, yes, there's a lot of memory, there's a lot of customers who fancy bells and whistles. But the program like R, it's not optimized.
What did
for
you
it.
just do?
You're gonna need some-
Okay.
I'll tell you afterwards.
Okay.
Hey folks, you know what I'm going to do here? I think I'm not going to record this section of the class, okay? Because I don't think the recording's going to go well.